Guys, I need your input. Can you see the slide? Let's focus
Yes,
on.
sir.
Okay, right. So we just talked about it, right? The most important things for electricity foundations is this four. We already checked out this slide yesterday. It's about electric current, electric resistance, potential difference, and EMF. Potential difference and electromotive force corresponds to energy, the reason for movement of electrons in an organized fashion or supposedly organized fashion. Electrical resistance is the reason why electrons slow down, why are they not running around very fast. And electric current corresponds to how many electrons or how many charged particles and how fast they are moving. If you simplify these concepts in this fashion, it becomes very easy. Textbooks definitions are important for your exams. You have to do that. But for understanding, this kind of method is much more useful, guys. Okay, so let's think about electric current. Now, this particular thing that you're observing right now, imagine it's a metal block or metal pipe or whatever, not metal pipe, it's a metal rod. The difference between pipe and rod, pipes are hollow. There's a gap, air gap in between. Rods need not have, I mean, they don't have any gap. It's a solid piece of metal. And imagine, I want you to imagine standing here at this location, at this cross section, okay, at this particular cross section, and you're observing what's happening inside the wire. You're like a miniature version, right? Very, very tiny guy. You're small. You have a chair, you're sitting on the chair, and you're able to see what's happening inside. So this is called, I mean, Einstein used to do this a lot. Einstein, he's not an experimental guy. He was not into empirical thing. It was all about theoretical problems. He used to imagine everything in his mind and derive theories about it. Okay, so I want you to try something. We are not doing practical experiment, but an experiment with your thought, right? So imagine you're sitting here and you're able to see this particular cross section. You can see that circular cross section over here. You're able to see that particular thing. And what you're doing is, imagine you're using a stopwatch, and you decided that you'll observe that particular cross section for 1 minute. So you'll be observing for 1 minute or maybe 1 second. It doesn't matter anything. The value should be 1 minute or 1 second or whatever. So you're observing it for 1 second, let's say, and all you're doing is you're counting number of charged particles. If you want to simplify, we can call electrons. But charged particles is more generalized version. But when you talk only about a metal wire, you can simplify it as electrons. Now, let's simplify it. You're holding your stopwatch and you're only checking for 1 second. And what you're doing is you're counting number of electrons that travel from left to right into this circle and right to left into this circle. Okay, let me give an example. So when you're doing this for 1 second, if you count completely, let's say from left to right, you saw 10,000 electrons passing through. Okay, 10,000 electrons passing through. And at the same time, the things that are moving from right to left, of course, some of the electrons are moving in this direction. From right to left, let's imagine only 1,000 electrons are moving through, 1,000. Now the difference in that count is 9,000 electrons from left to right. So that is what this N corresponds to. The electric current is defined as Q by T, that's given in your textbook. Much elaborated version is N into small q by T. N into small q by T, where N is the net number of electrons passing through a cross-sectional area of the metal rod or whatever. So let me repeat whatever I told you. Let's say from left to right, 10,000 electrons are moving, and right to left, only few thousand electrons are moving. So you don't count them as 11,000. You subtract them because the net movement is only 9,000. So among that 10,000, 1,000 got cancelled with the bottom one. So among this 10,000, 9,000 are passing through, 1,000 got cancelled with the right to left movement. You can imagine it like that. Okay. So the net number of electrons passing through is 9,000. And since we are speaking them as electrons, you just have to put the charge of an electron. You know the charge of an electron, minus 1.6 into 10 power of minus 23 coulombs, all that. Okay. And the time period that you had was 1 second. And this n into q is the total charge. N is the number of electrons, q is the charge of a single electron. When you multiply those, you get the total charge. It's like what is the cost of total number of chocolates? One chocolate is 10 rupees into 100 chocolates. 10 into 100 is 1000 rupees. That's what I just told you. Number of electrons into charge of a single electron. So when you do that, you get this total charge, capital Q, divided by total the time period that you used. That's 1 second. So I is given by Q by T, where yeah, I can see the chat window getting highlighted. Let me complete this and I'll check it out. So charge, units of charge is coulombs, okay, coulombs per second. Units of time are seconds. So coulombs per seconds is always amperes. So that's 1 ampere. Okay. Coulomb per second is amperes. So one thing I want you to remember is whenever a unit comes from a scientist, let's say Newton, units for force is newtons, right? So you have to use capitals. When units are from scientist names, you need to use capitals. And if the units are not from scientists, let's say the unit for distance is meters, right? I'm talking about the SI system. Meters. Meter is not, there's no scientist with the name meter. So meters can be written as small m. Okay, just remember this convention also. So all in all, we discussed the theoretical way, wherein you just have to count the number of electrons passing through the cross section, and small q is the charge of a single electron. And why is this important? Because if you take an electrolyte, a chemical, a liquid, in that electrons would not be moving. If you take the solution sodium chloride, then sodium ions and chlorine ions will be moving. There it's completely different. You have to consider the charge of chlorine ion actually, okay, not electron. So here we are talking about a metal block, so we are focused only on the electrons, and T is the time period. So all this is theoretical way. Now, when it comes to practical, whenever you hear the word electric current, I want you to remember two things. How many electrons, how fast are they moving? If there are more electrons, let's say you have two wires, wire 1 and wire 2. In both the wires, let's imagine electrons are moving with the same speed. But in the first wire, there are 100 electrons moving. In the second wire, there are only 10 electrons moving. So the first wire has more current because more electrons are moving, because charge is in the top. As you can see over here, Q is the charge that's in the numerator. More charge, more current. Okay. Now let's talk about the second thing. I have two wires. Both the wires have same number of electrons, 100 electrons and 100 electrons. But in the first wire, electrons are moving slow. But in the second wire, electrons are moving very fast. So which wire will have more current? Is it the first wire or the second wire? Anyone with answers? Same number of electrons in both the wires, but first wire has the slow speed electrons, second wire has fast speed, I mean lot of speed electrons. So which one will have more current? The wire in which electrons are moving fast. Why? Because electric current is related to time period inversely. If electrons are moving fast, they are taking less time. So less time, more current. Reverse relation, guys. I and T are related reversely. If they are moving fast, they are taking less time. When they are taking less time, there is more current. If electrons are moving very, very slow, they are taking more time. When there is more time, electric current is less. Okay. So all in all, you have to remember this. Electric current is defined, I mean, practically, whenever you think about electric current, two things. How many electrons, how fast are they moving? Large number of electrons, lots of current. Fast moving electrons, lots of current. Okay, that's the conclusion of this discussion. And I have a question I was asked to repeat. Okay, guys, you need to tell me which portion you want me to repeat. I think have Amarnath, It's you wanted me to repeat something, sir, once again. That was your message. If you please tell me what to repeat, I'll repeat it. You can switch on your mic, Amarnath. Okay, Amarnath isn't responding, right? What about others? Is this concept clear? Electric current? If there's any question, we can address it right away and we can move on. Anyone with questions? All right, so let's move on. And guys, are you listening? Is it audible? That's what the question right now, because I'm not hearing any response. Anyone in chat window? Yes, if you're listening to me, if you can hear whatever.
Yes, sir.
Okay,
Yes,
wonderful.
sir.
Yes, sir, you are audible.
Okay, all right. Thank you. Thank you. Right, so that's about electric current, guys. I hope you got the theoretical way, like the textbook, and also the practical way. Now let's move on to electric resistance. I know electric resistance should come. Oh, I'm sorry. I mean, before electric resistance, I want to talk about, let's say, 200-year-old confusion in electricity topic. Current electricity, there's a confusion. Even till date, many people get confused. Some people use one convention and other people use another convention when they write textbooks. Even professors have this problem actually. So not everyone follows the same thing. So I want to talk about that particular thing. In fact, when you talk about the direction of electric current, there are two directions possible. Okay, one is called the direction because of conventional current, and another one is electron current, conventional current and electron current. Let me show a particular slide. From there you can, I mean, hopefully I want you to get confused and later I want to clear that confusion. Okay, so now observe this battery. Observe this battery. And okay, let me do that. I want to ask a question. Let me do something else before that. I'm drawing a very simple circuit. So that's the battery. I'm closing the circuit. It's a copper wire, obviously. I'm not using any bulb. Even if I don't use a bulb, still the electrons will flow. Okay. You don't need a bulb because here the copper wire is using that energy. If you remember from our yesterday's experiment, we spoke about battery as the energy supplier, a bulb as the energy consumer. Even though you don't have a bulb, this copper wire itself is the energy consumer, because you need to have, since electrons have to move in this copper wire, some energy will be wasted. So that's why we are calling it an energy consumer. Okay. Now, what I want to ask you right now is, this is a metal wire, so only electrons are moving inside, right? Electrons are the only things moving inside. So my question is, why are the ions, let's make it simple. I mean, let me show you a small section over here. One second. Yeah. Now, if I take one copper atom from this wire, that copper is actually divided in this fashion. That particular copper is divided as, it's not copper plus 2, guys. I'm using copper plus 1 and 1 electron. So each copper atom is only donating 1 electron to this society of the wire. So each copper atom is giving 1 electron. So in fact, in this wire, there are both positive charges and negative charges. Copper plus 1 is the positive charge, electron is the negative charge. Now, as soon as you place this battery, we discussed yesterday that electrons move in an organized fashion, not perfectly organized, but overall in an organized fashion. So electrons are moving all the way around. Okay, but what about copper plus ions? Are they moving, or do you think they're stationary at the locations, their own locations? Once again, we already know that electrons are moving around because of the battery. Are the copper plus ions, Cu plus ions, are they really moving? That's my question. Okay, I got Amrit giving me the answer as stationary, and Hasini has also given me the answer of stationary, but she added something else for me. She said it vibrates. Wonderful, wonderful, both of you guys. And Hasini, of course, your girl. So Hasini and Amrut, they actually summarized our discussion yesterday. Copper ions are not moving essentially. They're almost stationary at the location, almost because they vibrate. And the reason they vibrate about their mean position is because of the outside temperature. Outside temperature make everything vibrate. Even the atoms in our body are actually vibrating. When the temperature in the room increases, the vibration increases. When the temperature in the room decreases, vibrations decrease. Okay, so that's what is the, I mean, whatever you gave. And now I want to ask another question. Why are they stationary overall? Why are these ions, the metallic ions, stationary? Why can't they run around like electrons? That's my question. Okay, Cu plus ions are fixed in lattice. That's Amrit's answer, the lattice structure. Now let's imagine, and by the way, that lattice structure is also an imagination. Since everything is stationary, okay, let me show you that old slide once. Okay, so this was and we discussed about it. This is the lattice structure. Electrons are the only one moving. They're fixed in their lattice structure. That's the point that you are giving to me. Let's say they're not fixed. Okay, there is a small possibility of movement. Even with that, do you think a battery can really move such a heavy mass? Now you know about electron, right? Electron is extremely lightweight. But when you talk about copper, the number of protons in copper is 29. Is it right? What is the atomic number of copper, guys? Yeah, it's 29, right? Scatti, Wickerman, Fekoni, Cousin. Ever heard this? Guys, have you ever heard this statement? Scatti, Wickerman, Fekoni, Cousin. Very good. Yeah, Scatti, Wickerman, Fekoni, Cousin means scandium, titanium, vanadium, right from 21 to 29. Okay, so all those 21 to 30. Right, copper is 29. So it has 29 protons and it has, let's say, 29 electrons. We are talking about neutral. So since one electron is donated, we can, let me write it over here. Now, one copper plus ion, this is the mass. I'm talking about mass. I want to analyze that. It has 29 protons. And let's say we have only 29 neutrons also. 29 neutrons. And let's say 29 electrons. I'm talking about a particular isotope of copper, which has 29 protons, 29 neutrons. And since it's a copper plus ion, it already donated an electron. So it has to be 28 electrons. Okay, so 28 electrons, that's a negative charge. Now, here you just have one electron, which is extremely lightweight. It can move around because of the battery when you connect a battery. But in order to move copper, our batteries are impossible. It's impossible to move copper ions because the ratio of masses. Do you know the mass ratio of proton and electron is almost 1800 times? That means you have a weighing balance. On one side, you have a proton. Other side of the balance, you should put 1800 electrons to have it balanced. It's 1800 times heavier. So that's the reason our batteries, whatever we are using, however powerful the battery, even that could give you 20, I mean, let's say the 220 volts that we have with us at our homes, those cannot push these copper ions or any ions actually, because they're extremely heavy. Okay, so we actually concluded from all the discussion a single thing, that only electrons move inside the wires. The metallic ions only vibrate. That's the conclusion of that whole discussion. Okay, now let me ask you a question. Electrons are everywhere. I want to use some dots with red color. I'm only using a few of those. Electrons are everywhere in this wire. Now, I want to ask you one question pertaining to the movement of the electrons. Which direction do you think the electrons are moving? Are they moving from battery positive to negative? Let me highlight that. Are electrons moving from battery positive to negative in this direction? Or do you think electrons are moving from battery negative to positive? Is it from battery positive to negative or battery negative to positive? That's my question, guys. Let me check the chat window. So Amrit gave me the answer as negative to positive. I also have another one, Hasini, giving it as negative to positive. Opposite to the electric current direction, that's by Hamsika, negative to positive, Vishnupriya. Good job, guys. You already know this, but still I want to elaborate. I'm such a teacher. I want to make sure everyone in the class, not only the brightest, not the brightest, but who are actively involved, I want everyone, even who are not actively involved, I want them to understand the concept. That's what I'm going to do. I'm going to explain the reason, and hopefully whoever knew the answer, you also it's a good chance for you to revise the reason behind this. Okay, now let's look at the reason. This is battery positive, right? I'll use black. Guys, this meeting will end in 10 minutes, it seems. So I think our original plan, you'll get an extra 2 minutes break, I guess, in between. I'll immediately say, I mean, what we can do is we can come out of it and you can redo it. I think you're already accumulated with this, right? The same link, you can use it, I hope. Okay, right. So let's continue with this discussion. Now, this is battery positive and battery negative. Battery positive, it's a positively charged thing, and electrons are all negatively charged particles. So obviously what happens, the negatively charged particles will be attracted towards the positively charged plate. So all the negative charges will be moving in this direction. Okay, and here this is negative, your battery negative is a negatively charged plate, and electrons are also negatively charged. So negative negative, we already know repulsions, just like magnetism, it's repulsions. So what happens, all these electrons get pushed out over here. So the electrons are pushed from the negative plate and they're attracted towards the positive plate. So the electron movement is from battery negative to battery positive. Okay, please remember this. This is also called electron current. It's not the conventional current, guys. I spoke to you about two types of currents, if you remember. One is called the electron current and another one is called conventional current. Electron current means you're following the direction of the electrons, and that is from battery negative to positive. Now let me use another color, the blue color, and this is called conventional current. The electric current that you're looking in your textbook, whenever you see electric current, it's actually called conventional current. Its direction is always from battery positive to battery negative. Direction of electric current is from battery positive to battery negative. It's actually called conventional current. And electron current is reverse. You're following electrons, and electrons always move from battery negative to battery positive. Okay, so these are the two types of currents, and this is a massive confusion. Some textbook authors actually use the entire textbook. They actually write initial itself. Whenever I use the word electric current, I actually mean electron current. They mention it in front actually. If it is not mentioned, that means they're talking about conventional current. And our 10th class textbook, it's all about conventional current. So whenever you see the word electric current in your textbook, it means conventional current, where current is defined as current direction is defined as from battery positive to battery negative. All right, so that's about conventional and electron current. Okay, exactly, Amrit. Whatever I spoke about, Amrit gave me the same answer. Negative terminal pushes the electrons, repels, and positive terminal attracts the electrons, because positive attracts the negative. So before we move on to the next part, it's not part of your textbook. I want to know from you if you are interested or not. Do you want to know the reason behind this confusion? Why two things came into picture? Why did the scientists bring up conventional current and electron current? Who is the reason? Who is the culprit behind it? The historical perspective. If you are interested, we can speak about in 5 minutes, or maybe not 5 minutes, a bit more. Otherwise, we can move on to the next concept of resistance potential difference. So I'm waiting for your answers, guys. Are you interested to know why this confusion arose? Okay. Few more answers. Yes, no, you can feel free to answer. Okay, I have Niyati, Hamsika, Hasini, Samra, everyone giving me answers as yes. So let's look into that also. Okay, I want you to know why this confusion. As I told you, history is a beautiful thing as long as you don't have to remember the dates. As a kid, I used to hate history, guys. Frankly, the only reason was more than those beautiful stories, the focus was laid on the location. It was laid more on the date. Is it Tuesday? Is it Saturday? Whatever it is. So that I really hated history. But once I came out of the school, I started reading more and more about history because I'm least concerned about exams. I'm more happy with actually focus laid on the stories. So stories are always wonderful, right? So this is one story that I'm about to talk to you about. Okay, whatever we discussed, this is the summary, guys. Current flow, we define actual electric current or the conventional current as from battery positive to battery negative. But in reality, this wire does not have any positive charges moving inside. Actually, the only things that are moving inside are the electrons, and those electrons are moving from battery negative to battery positive. And if you follow that direction, we call the current direction as electron current direction. Okay. Now, after this discussion, I want you to think about something. I want you to know this. Okay, it's a general cough, not corona cough. Don't worry. It's like lack of water. I need to have a sip of water. Uh, the thing is, after all these discussions about these two currents, I want you to kind of remember all this discussion, but don't focus too much on it. So I don't want you to get confused in your exams. Whenever they point out electric current, I don't want you to confuse. Should we follow electron movement or should we actually follow the current movement? All such confusion should not come to your mind. So let's enjoy this discussion, but always remember only conventional current, where current is defined as starting from battery positive and closing the circuit towards the battery negative. Okay, great. We have 3 minutes, and the culprit is again the great Benjamin Franklin. So Benjamin Franklin actually gave this reverse direction. Okay, because of that reverse direction thing, everyone in the world is actually using the wrong notion. Even though we know it is wrong, it still continued because we are used to it. And during Benjamin Franklin's time, when he gave this particular sign convention, everyone else agreed because he's super famous. Just like what Archimedes did. Archimedes discussions, Galileo had to. Galileo broke those conventions almost like 3,000 years later. So rather than science, their persona, their the charisma, that was actually the culprit. So these guys were super popular. So whatever is said by them or whatever was told by them, people accepted blindly. Same thing happened with Thomson and Rutherford's model. Thomson gave his model. Rutherford disproved Thomson's plum pudding model. If you remember the watermelon plum pudding model given by Thomson, Rutherford, with his experiments, he disproved it. Even after disproving, scientists did not care for it because they were kind of, Thomson was their hero, okay, like the god in one sense. They even with proof they were not ready to accept. So that's the problem with too much popularity. Other people take it for blindly, okay. So the Benjamin Franklin experiments, and before we do that, these are some of the things he invented. You already know the bifocals that he's wearing, and this is actually a kind of musical instrument he created. And this one is an old age GPS. You know GPS, right? Your phone has it. Google Maps. You move around. Your maps tells you where you are actually. So he actually designed this kind of a GPS. You could connect it to a cart or a whatever vehicle, and you can actually track the movement. Are you going left? Are you going right? From the start location till the end location, how many turns you have taken, everything can be recorded. It's a pure mechanical instrument, no electronics or anything in this, obviously, because we're talking about 1700s, guys. Okay, so that's Benjamin Franklin's experiment. So in order to understand this, I will briefly talk about this, and then our time will be, we will be off. We just have a minute more. So what happened was, Benjamin Franklin observed this experiment. We already spoke about this. Yesterday we spoke about rubbing amber to a cat's fur. You have to first make sure cat is provided fully with food. It's happy with belly full and it's sleeping. Then take an amber rock or amber pipe and start rubbing on the fur of the cat. And when that happens, that amber has suddenly attained the ability to attract small particles like husk, dust, or even small pieces of paper. It's a similar experiment where a glass rod is rubbed with a silk cloth. Okay, so when you do that, it both actually glass rod gets the ability to attract, and even silk cloth also gets the ability to attract some other particles. All right, guys, let's log off ourselves right now, and I want you to log in back. I'm ending this session. We'll come back and continue this discussion.